brings us to the question of how to come up with good heuristics. This is the baseline, bad heuristic. Okay, and in fact, this is where this picture that I showed you long back. For the longest time, planning people would think that the heuristics that would work would be cheap to compute heuristics. So the heuristics on this side, like set difference heuristic. Remember, you've seen this picture before, and you saw set difference. It didn't make sense to you then. This is where it's coming from. It's a cheap heuristic. But you can have more and more. H star is basically compute the plan, optimal plan from every state, and then use that as the length. And basically, people would only look for heuristics here, and obviously nobody was looking for heuristics here. But what really happened was the heuristics that are useful do this approximate reachability analysis of the kind that I was talking to you about earlier. And they actually take quite a bit of time. And in fact, in the textbook, they essentially show basically how to relax the problem using what's called planning graph heuristics. Basically, that once you do the planning graph heuristics, so I want to just, I'm not expecting you to understand completely, but I'm just trying to give you a sense. And they're not going to be exam questions on this. So if you want, instead of doing full reachability, exact reachability will be starting from the initial state and doing the projections, progression. Okay? That would basically tell you exactly how many states and which state is reachable from. For example, everything here is reachable from here after some number of actions. Right? But I want to do this approximately because doing this is costlier than just doing planning. Because planning only requires one path. Now I'm require the entire tree. So what we do is a strange thing in a sense. What it says is, instead of having these membranes between the states, each state is its own thing, I remove the membranes. It's like cell membranes disappear. Do you see what I'm saying? If you do this, you get something like this. This is not a state, but this is a union of all the states here and the union of all the states here. Union, element-wise union. So this is guaranteed to be an upper bound on anything reachable. So for example, if I'm trying to see whether P and Q can be done in 2 steps, and if P and Q don't exist in the 2 steps level, it can't be done. If it exists, it may still not be done. But if it's not existing, it can't be done. That's what upper bounds are. Using this, you then compute heuristics for planning. And that winds up being extremely useful. I don't know where we are, but so in fact, as I mentioned, if you look at the end of the textbook, and the end of the chapter, you'll see that that whole particular planning graph heuristic was based on something we did in this class 15 years back, essentially, which is this planning graph based. But the idea is using approximate reachability analysis to get an estimate of the length of it. Okay? In particular, like one simple idea that actually you can probably understand is this idea called relax plan heuristic, which essentially says ignore all the deletes for actions. If you ignore all the deletes for the actions, then planning problem is easier to solve. It's still not zero cost, but it's easier to solve. And that would be called, delete relaxation heuristic. And many planners currently use that. And if you find the optimal plan for the delete relaxation heuristic, that will be an admissible heuristic for the underlying plan. And pretty much a lot of planners use that kind of thing. Yes?
So like when you were showing, when you combine 2 different actions like G and not G.
No, those are goals, G and not G.
Okay. If you computed like all the possible results from combining them together, could you figure out whether or not, could you make it admissible? Because like if you realize that when they combine with each other that...
No, the admissibility, this will be admissible in the sense that it turns out that finding optimal plan, ignoring deletes. So I give you actions. okay, and assume the actions on the add delete list format. Just act as if delete list is all empty for every action. Then try to solve the problem. Optimally, in terms of, let's say, whatever your cost metric is. That cost of that plan would be a strict lower bound on the current plan. In fact, one of the issues is if you are into heuristics from A-star search, much of that chapter 10 about the heuristics really kind of makes it a lot more connected to generating heuristics. And because a bunch of, as one of these pictures kind of that I went to quickly showed, bunch of things that happened in planning at one point of time was really, they used to be, planners would be like this. Every planner, on every problem, the search cost is exponential. Okay? And what changed essentially is even taking into account the computational improvements, essentially the big difference was using good heuristics to cut down the search. And the heuristics would use abstractions. In fact, every kind of idea, remember that we talked about pattern database heuristics at the end of that class, end of search class, pattern database heuristics have been used in planning. There are also other kinds of cute ideas that have been used called landmarks, computing, and the fact that irrespective of what plan you take, you have to go through certain states. Right? For example, if you're going by ocean, right? Irrespective of if you are on, let's say, in America, and you want to go to something in Europe or something, irrespective of what you do, you will have to go through Panama Canal. That's going to be a landmark. And so if the Panama Canal is going to be closed on the day that you expect to cross it, your plan isn't going to work. So the landmarks can be computed directly from the domain theory, where domain theory is these action descriptions. And using that, you can improve the speed of the search. Okay? So I will stop here. I basically wanted to kind of make you think about what you can get if you have, descriptions of actions which have these preconditions and effects. Some of these things are more natural. You get to think in terms of goal interactions. You get to think of different kinds of searches, and then you can also think of better clusters. And it turns out that these same kinds of representations can be used to do actions with the duration. Like, for example, an action takes 15 units of time. And in the beginning, it gives some effect. In the middle, some gives some effects. And for the entire region, it might also be giving some effect. This is called temporal planning. And you can do that too. You can do stochastic planning. Essentially, all the things that we did in atomic level can be done in these kinds of representations. Before I forget, this Friday, there's going to be a guy giving a talk, Ronnie Codron. He's going to give a talk. I'll send you a link to that. This guy is a researcher who actually will talk about these kinds of lifted approaches, these kinds of, actually the words that are used for these actions with preconditions and effects, they can be called factored approaches or lifted approaches. And I mostly looked at factored lifted approaches for deterministic planning. Ronnie Codron will talk about how to use those kinds of things for stochastic planning. And a whole bunch of, some people ask what we do in our group. A whole bunch of things I did until about 8 years back was this kind of stuff. In fact, that's why the chapter on planning basically cites a whole bunch of things that we did, including temporal planning, including heuristics, including. And then the other part is that link that I sent you, the one that we are more interested in. Now we're still using these kinds of planning, but when you have a human in the loop, and so the human might have a different precondition effect model than what you have. And so your plan might be different from what the human expects your plan to be. And if they don't see you doing the plan that they expect you to do, they'll be surprised. At which point, either you can do what they expect you to do, which is explicability, or you do what is easy for you and tell them why this is easy for you. By telling them your model of my actions is flawed in the following process, which is explication. Okay? Thank you.